Thank you, Jamika. Thanks for setting this up. I see a bunch of familiar faces here. Minjay, it's very good to have you here. Rob, Jim, Victoria. So Victoria, if you wouldn't mind introducing yourself, I'd love to hear how you found out about Shadow the Scientist. My colleagues will be joining me in just a few minutes.
Sure. Hi, I'm Victoria. I graduated from Arizona State last year with my bachelor's in astrophysics, and now I work for Lunar Reconnaissance Orbiter Camera. I do lunar geology.
Fantastic.
And I found out about this. I think I get emails from the Space Telescope Science Institute occasionally about things that are going on
Oh,
because I
perfect.
applied to something previously. So now I'm just on their mailing list.
Okay.
And I want to get my PhD in astrophysics in the coming years. So it just seemed relevant. Yeah.
That's fantastic. Welcome. Welcome.
Thank you.
And I'll almost everyone else here everyone else here I've met before, but welcome, Victoria. And what we'll do is I'll share my screen, and so we can see what the controls look like of the Keck telescope and the instrument we're using. I just want to make sure I see some of the control windows are not working for me. So let me I'm going to repeat. I'm relogging into the VNC, the virtual network computing software that lets me control the Keck telescope from my laptop. There we go. I've got everything going now. I'm going to share my screen. This session is being recorded. We post the recording on the Shadow the Scientist YouTube channel. Jamika edits it first. I think each of you has the capability of turning on your video and audio. That's but I just want you to be aware that we are recording. Rob and Jim are in Southern California, and Victoria, you said you're in Arizona still, or are you somewhere else now?
Yeah, I'm still in Arizona.
Okay. In the Phoenix area, this is where Arizona State is, or in a different part?
Yeah, so it's kind of interesting. Lunar Reconnaissance Orbiter Camera used to operate out of ASU, but we were recently bought by Intuitive Machines, which is a commercial space company. So now we're in downtown Phoenix.
Gotcha. Gotcha. And Minjae, you're located in Seoul, Korea, right? And it's what, 3:30 in the afternoon, 3:40 in the afternoon for you, is that right?
And now I'm actually in Daejeon, South Korea. Just research.
Sorry, say that again, Minjae. You got cut up for a moment. Say that again, please.
Um, actually, this is 3:30 p.m. in Seoul, South Korea. So
Yeah,
now I'm
3:30.
in Daejeon.
3:30 p.m. Okay, excellent. And are you in Seoul?
No, I'm in Daejeon and Kansas right now.
I see. I see. And your institute is called the Korea Astronomical Institute for Science and Technology? No, Korea Advanced Institute for Science and Technology.
Yeah, exactly. You're correct.
Advanced, okay. And say that again, sorry.
Oh, I didn't know that.
Oh, okay. So Minjae is actually coming to Santa Cruz this summer to join our research group.
Yeah, exactly. I'm joining your recently.
Minjae, we're picking up a little bit of background noise from you.
Okay, wait a minute, please.
Okay, no problem. Yeah, so Minjae is going to be joining our research group. He's an undergraduate, but we have the Korea Advanced Institute of Science and Technology and UC Santa Cruz have a partnership, have a memorandum of understanding, so that students from our partner institution can visit us over the summer and do research. We can have student exchanges. So Minjae is going to be in our research group at Santa Cruz this summer. And with that, let me share my screen. And I'm going to share my whole screen, but there are 4 control windows that we'll be looking at. You'll see at the top it says control 0 right there. Can you see my cursor by any chance?
Yes.
Yeah, okay, good. So this is the control 0 window. This next one is control 1. This third one is control 2. And the final window is called tell status, which shows us the status of the telescope. This is where the telescope is pointed, the RA and deck, which object we're focused on right now, which is an ultra-diffuse galaxy. That's what UDG stands for, ultra-diffuse galaxy number 19. In the next generation Virgo cluster survey, NGVS is the next generation Virgo cluster survey. That's what our research team tonight is part of that survey team. It's a large survey team, and a subset of that team is using the telescope tonight. We're trying to get a spectrum, very long integration spectrum, quite literally 3 nights worth of exposure time on this one galaxy, which is, because it's very faint, we're trying to measure its spectrum to see if it's dark matter dominated or not. That's sort of the main goal of this research. You'll meet some of my other research colleagues from this project in a few minutes. They'll join the Shadow of the Scientist session. Now, one of the things that I failed to share is the sound feed from the telescope. So I'm going to stop my share for a moment, restart it with sound. I always forget to share with sound, but now when the next exposure reads out and there's an automated message from the telescope system, you'll hear it. So these telescope and instrument controls feel very, very much like, well, you're controlling many, many aspects of the telescope and instrument. And I'm making a distinction. The telescope is the Keck telescope here. It focuses light. The instrument is what does something with that focused light. In this case, it slices and dices the light in a couple of different ways. We're using really a 2-part instrument, an instrument that I say 2 parts because one of the first things that happens to the focused light is we use something called a dichroic to split the light into red and blue light. So at a certain wavelength, one of the light that has wavelengths longer than that wavelength goes straight through, and light that has wavelengths shorter than that wavelength gets reflected into a different path. So the wavelength is around 570 nanometers. At that point, we create a split. So light that's longer than that goes into one instrument. Light that's shorter wavelength than 570 nanometers goes into a second instrument. And the 2 instruments are called KCWI and KCRM. KCWI takes the shorter wavelength light, and KCRM takes the longer wavelength light. And if I show you these 2 windows here, you'll see that everything is in blue here. This is because this is, we show it in blue to remind ourselves that this is the shorter wavelength light. This part is shown in red because it's the longer wavelength light that goes into, so you're seeing KCRM over here, and the red arm of the instrument. It says it's actually now called KCWI red and not KCRM, KCWI red. And this is called KCWI. Let's see, what is this called? Should be called KCWI blue. KCWI blue right there. And what we're using is a combination of an imager and a slicer. What I mean by that is we take a rectangular region of the sky and obtain, imagine taking a rectangular region of the sky and dividing it up into very thin slices, so that each slice is maybe an arc second wide versus something like 30 arc seconds long. So we take a region of the sky that's marked by, this maroon region here, and we divide it into thin slices. We take a spectrum of each slice. In fact, for each slice, the red light gives us a spectrum, the blue light gives us another spectrum. So we actually take 2 spectra from each slice. So in the end, we get a spectrum of every pixel within that rectangular patch, within this, not the blue, but I believe the maroon rectangular patch. I'm not certain of this. No, actually, I take that back. We get the green rectangle, which is the narrower rectangle. We get a spectrum of every piece of that green rectangle. This instrument has a couple of different configurations. We can observe a white patch of sky or a narrow patch of sky. There's a trade-off. If you observe a white patch of sky, you trade off, I think you trade off spectral resolution for area on the sky. So for this experiment, we are using narrower patch of sky and higher spectral resolution. Hey, Elisa.
Hello, Raja.
Hey, Elisa, I just wanted to be clear. The green region is the narrower field of view, right? That we are using now.
The smaller slicer.
Yeah,
We are using the blue one.
we're using the blue one, so the widest slicer right now.
Mm-hmm.
But for the twilight
Exposure
UCD observations,
complete.
we use the pink one.
Yes.
I see. So the green one is the narrow slicer, and we're not using that because we want as wide a field as possible, right? For UDG 19.
Exactly.
I see. What's the trade-off? When you use a wider field of view, is the resolution worse?
Is the resolution is worse, yeah.
Okay.
We're making the field of view twice and basically losing twice in resolution.
Factor 2 in resolution. I see.
DCD
In
readout
spectral resolution.
complete.
What spectral resolution are we getting with the wide format?
It is, well, I know it in sigma, but it is 32
yeah,
kilometers per second.
32 kilometers per second.
Yeah.
I
so
see.
R.
So R would be about 10,000 then, because it's 1/10,000th of the speed of light.
Okay.
Right, you said 32 kilometers per second
32,
is,
yeah.
yeah, 32 is roughly 1 part in 10,000 of the speed of light.
Okay.
So R of about 10,000. If we quote R in sigma rather than full width half maximum. Hey, Sangsun. So these are the members of our research team. Let's see, who do we have here? Sangsun.
Yeah.
Lisa. Take a moment to introduce yourself, please. We have a few participants in Shadow the Scientist today. We can go around the room to introductions if that would be helpful. So Sangsun, take it away. You start, then I'll bounce it to Elisa, and then we'll go around the rest of the room.
Hi, I'm Sangsun Lim. I'm research professor at Yonsei University in South Korea. So I'm a member of this observation. I'm investigating the globular clusters in these ultra-diffuse galaxies, and also I contribute to found these ultra-diffuse galaxies initially. So that's the reason why I'm here. So nice to see you guys.
Thank you, Sangsun. Elisa, take it away. Jim, I'll answer your question in a minute.
Okay, so I am Elisa Toloba. I am a professor of physics and astronomy at the University of the Pacific in California, Northern California. And I work on galaxy formation and evolution. And recently we have been, very excited about these very mysterious ultra-diffuse galaxies, and we are trying to learn about them in every possible angle. So we are doing these observations today using the largest ground telescope to do spectroscopy, but we also recently got a James Webb Space Telescope time to also observe this galaxy that we are observing today, doing a spectroscopy of globular clusters in this galaxy using the James Webb Space Telescope. Those observations will happen early next year.
And Elisa, that's in the fourth cycle of
That
James
is
Webb's
cycle
operation.
4 of James Webb.
Operation, yeah. So James Webb was launched in December 2021. And there was an initial period of what's called early release observations and early science, early release images, early release science. Cycle 1 has happened, cycle 2 has happened, cycle 3 is going on right now. Each cycle is a full year of observations that's open to the general public. It's highly competitive. I think it's about 10 to 1 oversubscribed. So cycle 4 hasn't started yet, but when it starts, we hope to observe this galaxy. We expect to observe this galaxy with James Webb. Let's keep going around the room doing intros. But before we do that, I wanted to point out how sort of connected our science team is. So one member of our science team who hasn't yet joined is Eric Peng. And he is based in Arizona, like you, Victoria. He's based in Tucson, though. And but he used to be a professor in China before that. And even before that, when he was a student, he was an undergraduate student at Princeton. And when he was an undergraduate student there, he was my first research student while I was a postdoc there. I'm talking about in 1992, so we're 33 years ago. Eric and I have been working with Sung-Soon and Elisa at various times. Sung-Soon, your connection is to Eric before you were connected to me, right?
Yeah,
tell us about that.
I was a postdoc of Eric.
With Eric.
Complete.
In
Okay,
China.
we're gonna get ready to move.
Yeah.
Okay.
Yeah.
So you'll see a script, in this window, we'll see a new script being typed in for a new set of observations.
Exposure complete.
You guys can hear the telescope sounds like exposure complete and things like that, okay? So it's reading out. You can see that this readout is not yet finished. And this readout is also not just about
DCD readout complete. DCD readout complete.
Those two were for the blue and red sides, the CCD readout complete. Object now, right? Wasn't this the first sky? Lisa, shouldn't this be object, not sky?
No, it is a sky.
We're starting with two skies?
No, we did already an object.
Oh, we already did an object. Okay. So we did one sky, then object, then this is now two skies.
Yes, you are correct.
Total of third sky tonight?
Sorry.
In total, it's the third sky exposure tonight then?
Yeah, we just start with one sky and the object, and two skies, one object, two skies and one object, something like that.
So this is the
Second.
This is the second sky. So overall, the third sky tonight, right? We started with a sky, then an object, then this is two more skies after that. Okay, got it. Okay, Minjae, would you like to introduce yourself real quick? And then if it's okay, I'll then send it on to Jim, Rob, and Victoria. Minjay, take it away, please.
So it's very honored to introduce myself to you, very good scientists and researchers. And I'm a undergraduate student at KAIST recently, and I decided to join into the Raja's group, Professor Raja's group at this summer, 2025. And I want to learn and do something with this fancy observation results and analyzing some kind of scientific results. So I want to learn more and deep about these observational results. And yeah, that's all.
Thank you, Minjay. Minjay, you'll be working with Keck data, but not with KCWI, KCRM, but with an instrument called DEMOS. And Elisa Sangsoon and Eric are very familiar with DEMOS. It's a slit spectrograph, multi-object slit spectrograph, not an IFU, not an integral field unit like KCWI. Your science project will be really working with what we call serendips. So we go after particular stars and we get their spectra, but very often, because we work in crowded fields in Andromeda and Triangulum, very often the slits that we use to target the stars we're interested in pick up extra stars, pick up sometimes 2 or 3 extra stars, often 1. Sometimes it picks up extra stars that are so faint that we can't get meaningful information, but very often it picks up extra stars that are as bright as the target. And so your project this summer will be to extract information on all the serendipitous sources that we have accidentally obtained spectra of.
Exposure complete.
While us getting their spectra was accidental, the spectrum is just as valuable as the objects we designed the slit for. But anyway, I just want to mention that to the group, and I know we've been talking about that a little bit, and I owe you some emails to go over some details of the project. And I might send you a chat to schedule something.
DCD readout complete.
For a Zoom call. Okay, Jim, I'm going to bounce it to you, please, if you wouldn't mind introducing yourself. And I promise I'll answer your question.
I'm not an astronomer. I'm a software programmer, but I just enjoy these sessions. I live in the LA area.
Thanks, Jim. But you're an astronomy enthusiast, and so it's through a session at Griffith Observatory in Southern California that you and Rob got connected to Shadow the Scientist.
Yeah.
Oh, thank you for joining. Rob, if you want to say a quick introduction, I'd love that.
Okay, I'm Rob Johnson. I'm coming from Los Angeles. I'm a mathematician, amateur astrophotographer, and a software engineer working at UCLA right now. As Raja said, I found out about Shadow the Scientist through Griffith Observatory, the All Space Considered. And I was a grad student at Princeton just before Raja was. That's about it.
Thanks, Rob. All right. Victoria, I'll come to you in a moment, but Min Cheng, I know you're joining our research team, or you're part of our research team, but you're joining the observations today. Do you want to take a moment to introduce yourself?
Okay, so hello everyone. So I'm a graduate student at Peking University, and today I'm going to watch your observation and learn something about how to use the Keck to do the observation. And my advisor is Eric Peng, and also Samsung advised me for my PhD project. So thanks everyone.
Thank you, Min Cheng. Thank you very much. And Victoria, last but not the least. Well, actually, I'm last, so you're second last. Please go ahead.
I'm Victoria. I have my bachelor's in astrophysics from Arizona State. I'm in Arizona now. I work for Lunar Reconnaissance Orbiter Camera, where I study the surface of the moon and I make data products for lunar exploration, and I hope to get my PhD in astrophysics in the next couple of years.
Thanks, Victoria. Please keep UC Santa Cruz in mind when you're looking at grad schools.
I definitely will.
All right, so Jim, you asked a very important question. Why is spectral resolution expressed in kilometers per second? There are multiple ways to express spectral resolution, and let me start by saying that one way to think of resolution is the degree of blurring. I find it convenient to think of it this way.
Exposure complete.
That is, let's say a certain pixel is supposed to see a certain wavelength of light. But what happens for practical reasons, for any spectrograph, the light that lands on a pixel isn't just a single wavelength, but it's a mix of neighboring wavelengths. And how broad that mix is, how broad a range of wavelengths are mixed into
DCD readout
a given
complete.
pixel, is a measure of spectral resolution. If it's a very broad range, that's low resolution. If it's a relatively narrow range of wavelengths that are hitting a pixel, that's called high resolution. Another way to think of this is, let's say we're taking a spectrum of something like the sun or a star that's like the sun, and it has a very sharp absorption in the spectrum. Intrinsically, there's a certain wavelength of light that is getting absorbed by elements in the atmosphere of the sun or a star. If we had a very, very high resolution spectrograph, that spike would be very narrow in wavelength, meaning you could measure the lowest point of that dip, and you could measure where the dip is half the minimum value. So that's called, you can measure the two sides on which it's gone halfway back up to the sort of flat level. And the gap between those two halfway points is called the full width at half maximum. In this case, really, it's a full width at half of the minimum. So those are ways in which one can characterize the resolution of a spectrograph. So often it's expressed just in angstroms, because if you're measuring the wavelength in angstrom, the degree of smearing in angstroms is a measure of spectral resolution. And again, the larger that number is in angstroms, the worse the resolution. The smaller the number is, the better the resolution. Now, it's very common to use something called resolving power, which is slightly different from resolution. Resolving power is the wavelength of light divided by the amount of smearing. So it's lambda divided by delta lambda. So that's a dimensionless unit. And in dimensionless unit, our resolving power is something like 10,000. And because it's a dimensionless unit, what we can do is multiply that by the speed of light. And it means when you multiply that by the speed of light, you get, because all Doppler shifts are measured in units of the speed of light. The delta lambda over lambda is equal to v over c, where v is the velocity. So it's a convenient way, if we consider resolving power, lambda over delta lambda, and take that as a fraction, multiply that into the speed of light, that tells us how much smearing happens in velocity space. So, in other words, if we had
exposure complete.
Let's say a galaxy or a star with an emission line at a certain velocity, it would get smeared out by that many kilometers per second. I hope that explanation was okay, Jim.
So I think what you're saying is it's an expression of
Exposure
how accurately
complete.
you can measure how fast this object is receding from us.
Yes, it's a measure of accuracy. It's a measure of how things are smeared out in velocity space. So if we're measuring Doppler shifts, which is something we're trying to measure for this galaxy, one way of thinking of it is
that's because of the redshift.
Because of the redshift. It's the smearing of the redshift. How much of smearing of the redshift happens? Now, there's intrinsic smearing of the redshift of the galaxy, which is what
DCD readout complete.
Sorry, I should wait for the instrument change, and I'll come back.
DCD readout complete.
So now we'll do an object exposure, I assume, right, Elisa? Elisa, didn't we want an object exposure here?
We are taking another sky.
Third one
This is the third sky. Yeah.
in a row?
Yeah.
How come we're not doing an object?
Because we are doing a sky, object, sky. That is our pattern.
But then why 3 skies in a row?
No, 2 skies in a row. We did sky, object, and now sky, sky. And the next is another.
Okay, I must have missed the. Okay. So this is overall our 4th science exposure of the night. So I'm very confused. Not counting the UCD. So Jim, this galaxy we're observing, UDG 19, its name is right there, UDG 19 over there. This galaxy we're observing is so faint that you really can't see it on this image or on this image in the background here. Very hard to see the galaxy. It's very, very uniform and low surface brightness. But what we're trying to do is take its light and look at the. Oh, I'm not sharing my screen. Am I? I thought I am sharing my screen. Aren't you seeing my screen? Oh. Are you seeing my screen change here, Joe?
Oh,
Are you
never
guys?
mind. I did something weird in Zoom.
Oh, no
My
problem, no
fault.
problem. Okay, no, it's okay, good. I'm glad you alerted me. Yeah. So what we're so the galaxy we're looking at is made of stars. Stars have absorption lines in them, generally, like stars like the sun have absorption lines. So when we get the collective light of all the stars in the galaxy, or many of the stars in the galaxy, not all, or all the stars in a certain section of the galaxy, I should say, when we take its collective light and we measure the spectrum, here's what we're hoping to learn. If the stars in that galaxy are rattling around rapidly because the galaxy has a lot of dark matter, and so there's a lot of gravitational tugging of the stars, then the different stars in the galaxy have slightly different redshifts from our perspective. Overall, the galaxy has a certain redshift,
Exposure
but different
complete.
stars have slightly different redshifts because they're rattling around within the galaxy as the galaxy is moving away from us. Now, the way that should manifest is the absorption lines, let's say something like a Balmer absorption line, H beta, the 4 to 2, 2 to 4 transition of the electron within a hydrogen atom from level 2 to level 4. That absorption line, which is at 486 nanometers,
CCD readout complete.
could be really broad if the stars are rattling around a lot, because the different stars have absorption at slightly different wavelengths because of Doppler shifts. And we are seeing we should see a very smeared out absorption line if the stars are rattling around a lot. If, on the other hand, all the stars are moving at roughly the same velocity, their absorption lines will be perfectly lined up, and we should see a relatively narrow line. So our goal is to measure the width of these absorption lines in the spectrum of this galaxy. And of course, part of the width that we are seeing is due to instrumental resolution, but we've chosen an instrumental resolution of 30 kilometers per second because we expect the intrinsic broadening of this galaxy to be much bigger than that. We expect the broadening to be dominated by Doppler shifts within the galaxy, not by instrumental resolution. If we had expected the galaxy to have very little dispersion and velocities, we would have chosen a much narrower we would have chosen a setup with a lower spectral resolution. Sorry, with a higher spectral resolution, lower number in kilometers per second. I'm sorry if I'm being confusing. Yes, we're hoping to measure the mass of the galaxy based on how smeared or unsmeared the absorption lines are. That's exactly right. And a rough formula for how we measure mass is m is roughly equal to sigma. I'm going to write this out as though I'm writing in LaTeX. Sigma squared r divided by g, where r is the radius of the galaxy, sigma is the dispersion and velocity. You can think of it like an orbital speed of the typical orbital speed of a galaxy. So v squared r divided by g has the right units to be mass, where capital G is the gravitational, universal gravitational constant. So we know the size of the galaxy, we know how big it is on the sky, we know the gravitational constant, we're trying to measure sigma. Now, how we get from this to dark matter is relatively simple after that, because if we can measure the total mass of the galaxy, because how fast the stars are rattling around is a measure of the total mass, how much gravity the stars are experiencing. If we then compare that to how much luminous mass the galaxy has, how much mass it has in the form of stars, and we do that just by measuring the brightness of the galaxy.
Exposure complete.
That tells us whether the galaxy is dark matter dominated or not.
May I ask a question?
Yeah, please.
So you said that you are just want to measure some kind of mass or kinetic profile using the spectrum information. Then, first of all, what is the exact definition of the mass and radius? Is it virial mass or
CCD
M500,
readout
R500?
complete.
We are trying to measure the virial mass of the galaxy, or dynamical mass it's called. We are measuring the mass. We are trying to get at the total mass, but it's based on modeling. You have to model the density profile of the tracers, which in this case the stars. We are not able to measure dispersion as a function of radius. We can get one number, a global dispersion. So it's somewhat model dependent. So it's difficult to get this accurate to within a factor of, let's say, we don't expect to get this to a precision of 10%, but if we can get this to an accuracy of 30, 40%, if this thing is truly dark matter dominated, then there's 10 times as much mass in dark matter than there is stars, 10 or even more. So if it's really dark matter dominated, it's not a subtle effect, and we should be able to measure it. But the mass modeling is not a super precise process.
Thank you for your answer.
Yeah, thank you. We're basically using something like Jean's theorem and measuring a Jean's mass for the galaxy. Sung-Soon, Elisa, did I get that right? How we're measuring mass? It's like a Jean's mass, right? We're measuring.
Sorry, Raja, we were making decisions on the other Zoom call. Sorry.
Oh, sorry about that. Are you okay now to answer the question?
Yeah, now yes.
So the mass we are measuring, I mean, assuming we get a good spectrum and we measure the velocity dispersion of we get a global number. We don't get it as a function of radius, right? We get one number,
No.
integrated number. But we're effectively using the virial theorem. We're getting a Jean's mass, right, in the end.
Yes. Yeah.
Minjay was asking about how we're determining the mass. Yeah, it's something.
Yeah.
What was this? Was it a difficult decision to make?
Oh, just how we are going to finish our observation.
Okay.
The last, because we think that the last the last exposure is not going to be full. So if we are going to take it anyways, or we're going just to stop like 4 or 5 minutes early. Yeah.
See. This is at the changeover time, right? At
Exposure
12:18 or
complete.
12:19.
Is it what? Sorry?
This will be at the changeover time at 12:19.
Yes.
Okay. We should ask Wei Cheng to give us 10 extra minutes.
Exposure complete.
We can reverse. He was asking us for 10 extra minutes. So, so Jim, Victoria, Minjae, and Rob, this is a split night. So we have the first half of the night, but the second half of the night is going to be a different science project, not using KCWI or KCRM. It's using a completely, they're using adaptive optics, and they're doing a
DCD
completely
readout
different.
complete.
So two completely unrelated projects on
DCD readout complete.
two completely unrelated teams as well. Okay, I'm going to wait to see what happens here. There we go, object. So you can see that the total exposure time on the blue side is going to be 1320 seconds, which is 22 minutes right there. And there'll be 4 of these 300-second exposures on the red side. So 300 seconds is 5 minutes. 5 minutes times 4 is 20 minutes. So we're doing a total of 20 minutes on the red side and total of 22 minutes on the blue side. And you can see this is 1 of 1, blue exposure 1 of 1. 1320 is the exposure time. So 1 exposure for a total of 22 minutes. And here it's 1 of 4, each one being 5 minutes, 300 seconds. That's what has just been started by this script. And each time it completes an exposure, you can see the exposure started on the blue side, 4% complete. You can see that, oh, ignore the 60 over here. The exposure time is 1320. When we use a script, this part is only for manual entry. We're using a script. So 1320 is the exposure time on the blue side. And on the red side, the exposure time, again, ignore the 180, is 5 minutes, 300 seconds. And it's going to do 4 of these exposures. This is what the spectra look like on the red side. This sort of barcode symbol is the spectrum of air glow from the Earth's atmosphere. There's relatively little air glow lines on the blue part of the spectrum. So that's why this part looks much cleaner. There's a few bright emission lines from the Earth's atmosphere, but for the most part, things are less crowded in the short wavelength part of the spectrum. I know we are approaching the, we're not far from the end of the hour. I've been talking and talking. Are there questions that you might have that you haven't asked yet? I see something in the chat. Yes, when I said rattling around, I meant, orbiting. The stars in these galaxies, the galaxy we're looking at is not a nice frisbee-shaped galaxy. It's more like a swarm. We think it's 3-dimensional in shape, meaning it's roughly spherical in shape rather than 2-dimensional as in flattened. In these 3-dimensional systems, elliptical galaxies are good examples of that. Generally, no 2 stars orbit in the same plane. That's what gives it this 3-dimensional look. It's like a swarm of insects, swarm of bees around a hive. Whereas when you have a planar galaxy, all the stars' orbits are in one plane. So they're very different behavior. And in the case of planar galaxies, what we measure is how fast that plane is spinning. Vera Rubin did this for spiral galaxies to measure dark matter in galaxies. When a galaxy is a swarm of stars, we measure what is called velocity dispersion, the spread of velocities, how fast. And that's what I meant by rattling around. Yeah, that is the variation in speed, the spread of speeds across the different stars that are in the galaxy.
Did you say yesterday that there were more Shadow the Scientist sessions this week?
There's 2 more, each of tomorrow night and the night after. So we have Sunday night, Monday night, tonight's Monday night, Tuesday and Wednesday nights as well. Slightly different times. So we had a 9 p.m. start yesterday. Sorry, I'm talking about Hawaii times. We had a 9 p.m. Hawaii time start last night, which was midnight Pacific. Tonight was a half hour earlier. It was 8:30 Hawaii, 11:30 Pacific. Tomorrow is another half hour earlier, 8 p.m. Hawaii, 11 p.m. Pacific.
Complete.
And then we'll go back to, on Wednesday night, we'll go back to 9 p.m. Hawaii, midnight Pacific for the start. But it's, yes, it's one 1 hour session each of these 4 nights. Same project, same instrument setup, same science team.
Oh, I guess somehow I didn't click on all 4 links.
I think that, yeah, I'm pretty sure we have sessions.
Yeah, I'm looking at the email.
DCD
and
readout
I
complete.
guess I didn't realize it was 4 different. So I'll go click those now. I probably won't be able to do Wednesday, but I could probably do tomorrow.
And I think Jamaica's invited a group, forgetting where they're from, but that's why we're doing a especially early start tomorrow. Forget which group is joining, but there's a particular group joining. Yesterday, we had a group of children from Hawaii, from the Big Island, who had physically visited the observatory before sunset, and then after by sunset, they had gone home and they had connected on Zoom.
They visited the facility at the bottom, or they went to
At
the
the
top?
bottom. They went to Waimea, to Keck headquarters. They were hosted by some of the staff at Keck headquarters, and the person who brought the group used to work at the observatory years ago. So it was her grandson's homeschool group that had visited yesterday. They were sort of middle school to high school range. So Minjay, I meant to ask you, I was wondering whether I could have a Zoom call with you, but in a few hours' time, something like it is 20 past 4 for you now?
Yeah, this is 4:22.
4:22. I don't know if it's too late for you, but it would be around 10 p.m. your time, 6 a.m. my time. I will have some time to talk
Oh,
then.
yeah.
Would that work for you? Is it not too
Of
late?
course I can.
Okay. What I'll
Yeah,
do
it's
is,
not.
okay, I'll send you a Zoom link in the chat right now, and I can also send you a calendar invite. That would be a good time to just discuss our summer research project. There's been a lot of exciting things happening, and I'm happy to share that with you so you feel prepared for your summer. And I'll send you a link in just a moment. Please give me a. Jay, give me another minute and I'll send it to you. Okay, I have to find the link for you. I'll put this in the chat. Vinjay, do you have the Zoom link then?
Yeah, I have it.
Okay, so it'll be oh, thanks, Jim. That's the time I'm suggesting. Vinjay, is that okay?
Yeah, absolutely right.
It'll be late at night for you. I apologize. I won't make you stay up so late every time. Just this one time.
Undergraduate student always sleep late time, so it's fun.
Okay, thank you. I'll send you a calendar invite with the same information. I'll do it right now. In fact, I'll do it so you can see it. So we'll do this.
Exposure.
You can see how full
complete.
my calendar is. It's pretty crazy. I'm just going to give it the project title like this, okay?
DCD readout complete.
Wait, your email address, I have to type in. What does your email address start with?
Oh, I can send you in this chat here.
Okay. Perfect. Thank you. Ah, I've got it. You should have a calendar invite now.
Yeah, I think so.
Okay. I'll see you on Zoom in how much time? Let's see. 5.5 hours from now.
Yeah.
Okay. So I'm going to prioritize our guests here. Victoria, did you have any questions before we hang up? And you're welcome to join again tomorrow night or Wednesday night as your schedule permits.
Sorry, you cut out. Could you repeat it?
I said that, we'll have another session like this tomorrow night and the night after. It'll be a half an hour earlier tomorrow night. So you're on the same time zone as you're on Mountain Standard Time right now, right?
Yeah, it gets confusing because we don't do the time
Daylight
change.
savings.
Is it like midnight for?
No, right now it's 12:30, same as you.
Okay, yeah.
We have the same time as you. So tomorrow our session will start at 11 p.m.
Oh, okay. Yeah,
It's
I
a
would love to join.
1 hour session tomorrow starting at 11. And then on Wednesday night, we start at midnight.
Okay.
And that'll be the end of our run. But we have
Are the
shadow
Zoom links the same?
sessions. Sorry, what? No, the Zoom links are different for each night. There's a different Zoom registration link each night. Because what happens is that helps us keep track of participants for the different calls.
Yeah, I thought they might be different. I just figured Victoria might need to know that.
Yeah,
Yeah.
they're different. So the Zoom registration link is different for each night. And it's the same process. You fill out a simple form and you get a Zoom link. Hopefully it's a simple form. It's just a few questions.